Hey everyone! Welcome back to the Science Enigma. Today, we are delving into the mind-bending realm of theoretical physics as we explore groundbreaking discoveries that hint at the existence of the multiverse. Strap in, because this is going to be a mind-expanding journey. Our story begins in 1964, when physicists Arno, Penzias and Robert Wilson stumbled upon the cosmic microwave background, CMB, radiation, and afterglow of the Big Bang. This discovery earned them the 1978 Nobel Prize in Physics and laid the foundation for a new era in cosmology. Arno Penzias and Robert Wilson, stationed at Bell Labs in Holmdel, New Jersey, were engaged in the setup of highly sensitive microwave receivers designed for radio astronomy observations. Despite their efforts, the duo struggled to eliminate background radio noise persisting in the receivers, an enigma as it seemed to emanate simultaneously from all directions. In a bid to unravel this mystery, Penzias reached out to Princeton University physicist Robert Dicke. Dicke proposed that the pervasive radio noise could be cosmic microwave background radiation, CMB, an ancient microwave radiation that permeates the entirety of the universe. However, this revelation also brought forth one of the most unexpected discoveries in recent times. Distinctive characteristics within the CMB may serve as the initial tangible proof we've encountered for the existence of the multiverse. Yet, comprehending this extraordinary assertion requires embarking on a journey back to the inception of space and time. According to the broadly accepted theory for the origin of our universe, for the first several 100,000 years after the Big Bang, our universe was filled with a ferociously hot plasma comprised of nuclei, electrons, and photons, which scattered light. By around 380,000 years of age, the continued expansion of our universe caused it to cool to below 3,000 degrees K, which allowed electrons to combine with nuclei to form neutral atoms, and the absorption of free electrons allowed light to illuminate the dark. Evidence of this, in the form of radiation from the cosmic microwave background, is what was detected by Penzias and Wilson, and it helped establish the Big Bang theory of cosmology. Over the eons, continued expansion cooled our universe to a temperature of just around 2.7 K, but that temperature isn't uniform. Differences in temperature arise from the fact that matter is not uniformly distributed throughout the universe. This is thought to be caused by tiny quantum density fluctuations that occurred right after the Big Bang. Notably, a particular location, observed from the southern hemisphere in the Eridanus constellation, stands out for its extreme coldness, approximately 0.00015 degrees cooler than its surroundings. This region, famously designated as the cold spot, initially led scientists to theorize that it might be a supervoid, characterized by a scarcity of galaxies compared to the norm. However, in 2017, researchers from the UK's Durham University Centre for Extragalactic Astronomy challenged this notion with their published findings. They posited that the cold spot isn't a supervoid after all. Rather, it could be indicative of the presence of alien universes. Durham professor Tom Shanks put forth a novel and, as he termed it, more exotic explanation for the cold spot. His proposal suggested that the cold spot resulted from a collision between our universe and another bubble universe. In this scenario, Shanks asserted that the cold spot might serve as the initial evidence for the multiverse, indicating the existence of billions of other universes similar to our own. Some physicists had previously pointed out that a collision between our bubble universe and another within the multiverse would leave an imprint on the CM. They emphasized that this imprint would manifest as a circular spot with either higher or lower radiation intensity. Schenck's proposition appears to align with these expectations, but could this distinctive feature truly be evidence of an infinite multitude of universes existing beyond our own? Today, the principles governing the multiverse are explained by three primary theories. First, the Copenhagen Interpretation, second, the many worlds or branches of the wave function interpretation, and third, the parallel branes of string theory. For now, we'll set aside the discussion of string theory and concentrate on the former two explanations. The collective sum of all potential states in which an object can exist is referred to as its coherent superposition, constituting what is known as the object's wave function. In the realm of quantum mechanics, a seamless and entirely deterministic wave function is essential. This mathematical expression communicates information about a particle by presenting numerous possibilities for its location and characteristics. Simultaneously, it demands a mechanism that actualizes one of these possibilities while nullifying all others. Divergent views exist regarding how this actualization occurs. But in the prevalent Copenhagen interpretation, it transpires through the observation of the wave function or its interaction with some component of the classical world. This interaction leads to the collapse of the probability or wave function, compelling the particle to assume a singular state. Formulated in the 1920s by physicists Niels Bohr and Werner Heisenberg, the Copenhagen interpretation contends that a particle lacks a material existence until it undergoes measurement or observation. The Copenhagen interpretation was essentially a makeshift solution, and for many, an unsatisfactory one at that. In 1935, Austrian-Irish physicist Erwin Schrödinger highlighted the shortcomings of the Copenhagen interpretation with his renowned thought experiment, commonly known as Schrödinger's cat. In this hypothetical scenario, a cat is confined within a sealed box alongside a small amount of radioactive material and a Geiger counter. Should the Geiger counter detect the decay of the radioactive substance, it triggers the release of poison gas, resulting in the cat's demise. While the box remains sealed, the cat exists in a superposition of being both alive and dead simultaneously. The resolution of this paradox occurs only when the box is opened, compelling the cat into one definite state. Schrödinger pointed out the absurdity of this scenario, emphasizing that the principles of quantum superposition cannot be applied to larger entities such as cats, as it defies the fundamental impossibility of an organism being simultaneously alive and dead. Consequently, he argued that the Copenhagen interpretation must inherently be flawed. Several alternatives to the Copenhagen interpretation emerged. For instance, the hidden variables approach advocated by Albert Einstein and David Bohm. Among others, proposes treating the wave function as a provisional solution until physicists discover a more satisfactory framework. Later, Heisenberg suggested that the problem lies in our understanding of reality itself. He posited that the wave function represents an intermediate level of reality. The most straightforward approach may be that of the many worlds interpretation, MWI, which was initially proposed in 1957 by a Princeton University graduate student named Hugh Everett. Under the mentorship of John Archibald Wheeler, who envisioned the universe as a dynamic, subatomic domain of quantum fluctuations termed quantum foam. Everett presented his theory in his dissertation titled The Theory of the Universal Wave Function. In contrast to the Copenhagen interpretation, Everett argued that the universal wave function is genuine and doesn't undergo collapse. In that case, every possible outcome of a quantum measurement is realized in some world or universe, and by that logic, there must be a very large, or infinite, number of universes. Later on, Stephen Hawking's final research paper was released in 2018. It was a collaborative effort with Thomas Hertog, a professor of theoretical physics at KU Leuven University in Belgium. The subject of their work centered on the concept of the multiverse. In their paper titled A Smooth Exit from Eternal Inflation, Hawking and Hertog proposed the idea that the swift expansion of spacetime following the Big Bang might have occurred repeatedly, resulting in the creation of numerous universes. This proposition expanded upon inflation theory, the prevailing notion that the Big Bang did not mark the absolute beginning. Inflation theory posits that preceding the Big Bang, the universe harbored energy inherent to space itself, driving an exponential expansion of space. This energetic expansion ultimately triggered the Big Bang. However, owing to the quantum nature of inflation, it would have concluded at varying times in distinct locations, allowing the space between these locations to persistently inflate. Consequently, regions of space would exist where inflation ceases, leading to the initiation of a Big Bang. Yet, these distinct regions could never intersect, as they remain separated by expanses of inflating space. In an interview, Hawking expressed reservations about inflation theory. He stated that the usual theory of eternal inflation predicts that globally our universe is like an infinite fractal, with a mosaic of different pocket universes, separated by an inflating ocean. The local laws of physics and chemistry can differ from one pocket universe to another, which together would form a multiverse. If the scale of different universes in the multiverse is large or infinite, the theory can't be tested. Instead, the duo posits that the universe, particularly on its grandest scales, possesses a smooth and finite nature. Their theory employs the concept of holography, elucidating how physical reality in certain 3D spaces can be mathematically condensed to 2D projections on a surface. Utilizing this concept, they succeeded in reducing eternal inflation to a timeless state, defined on a spatial surface at the inception of time itself. Applying their novel theory, Hertog and Hawking anticipate that the universe emerging from eternal inflation is, in reality, finite and markedly simpler than the infinite fractal structure projected by the prevailing theory of eternal inflation. Hawking elucidated, "We are not down to a single, unique universe, but our findings imply a significant reduction of the multiverse, to a much smaller range of possible universes." This not only renders the theory more predictive but also testable. If Hawking, Hertog, Everett, Laura Mersini-Houghton, Tegmark, Green, and a plethora of other physicists are correct, then in some alternate universe, precisely at the moment you are watching this video, Hawking is engaged in lively discussions about physics while walking and talking. Let's remain hopeful. In conclusion, the first ever evidence of the multiverse is a thrilling chapter in the ongoing exploration of the cosmos. While we're not ready to pack our bags for a journey to a parallel universe just yet, these discoveries open up new avenues of inquiry and challenge our fundamental understanding of the universe we call home. Thank you for joining us on this cosmic adventure. If you enjoyed this video, don't forget to like, subscribe, and hit that notification bell for more mind-expanding content. Until next time, keep looking up.